Say welcome to the 12th open lecture. What we do in the 16G organization. At this time, it's about experimental technologies for 6G towards network intelligence. This is mainly targeting the interest of testing of how to evaluate 6G technologies and so on. I'm Josef Eichinger. I'm chair of 16G Working Group 4 since a while, since the start of 16G was actually 5 years ago. We have now the fifth birthday. I'm also head of the 6G research and prototyping department in the Huawei Munich Research Center, but now it's renamed to Huawei Heisenberg Research Center. So you can also reach me anytime. I'm also visible in the internet, and I'm happy to get any kind of information from you or questions. What I'm doing as head of research and prototyping, just to say a few words, and also in Working Group 4, we do some testing, we do proof of concepts. We have also at the moment running nice experiments about ISAC, 6G ISAC, and ISAC will also be mentioned here in this talks here. We are also as 16G Working Group 4 very happy if anybody member of 16G is raising an interesting challenge to us and to the members of the work group, but also to the entire members of the 16G. I also want to highlight that we have a lot of white papers recently published, and we also, as 16G, have a summit in September, and please check out the invitations and register in time to the summit. Now let's start immediately with the first presenter, because Andreas has a bit time pressure. Please, Andreas, maybe you can introduce yourself better than me.
Yeah, thank you, Josef. I'm very happy to be part of this open lecture on experimental technologies for 6G. So as Josef introduced, I'm Andreas Kassler. I'm professor in computer science at Deggendorf Institute of Technology and also at Karlstad University in Sweden, and both are members of the 16G. So today I'm going to talk on AI time series model benchmarking. And maybe I can share the screen, right?
Yes.
Okay. Can you see the screen?
Yes, the floor is yours.
Okay, thank you, guys. So as we have all witnessed, basically we have seen an evolution of our telco networks over the last 30, 40 years. So in the 2000s, we had closed hardware platforms that were proprietary, were very difficult to innovate with network programmability and network virtualization. In 2010s, we got the decoupling of control and data plane and hardware and software. Many things become softwareized. And from network management, we still do based on some rules, and we do like reactive, and some issues happened, and we try to solve them reactively. In the last decade, we were going towards 5G and cloud nativeness. We containerize many of the network services. We have microservices, deploy them on the cloud, use orchestration. Still, I would say we use a lot of rule-based control loops and traditional algorithm. And now towards the 6G in the 2030s, maybe not so far from now, we are going towards AI nativeness. So AI nativeness means that we have AI embedded capabilities in our networks that run on AI native infrastructure. We have intelligent and autonomous control, and we have proactive intelligent network management characterized by hundreds to thousands of AI models that somehow try to optimize our network. So in order to build this AI nativeness, currently we are on the verge to build an AI native telco cloud, which for me has 4 pillars. First one is the AI infrastructure. So that is the hardware infrastructure that is empowering this revolutionary shift towards AI nativeness. That's a lot of AI, DPUs, tensor units, AI hardware accelerator. Then we have the AI agents. So the AI agents are software agents that try to reason about something and propose some solutions. Then we have a digital twin, which is a softwareized representation of our physical hardware in the digital world. So a digital twin, if it's synchronized well with the real network, can be used to do what-if decisions. And then we have this bunch of AI models as a service. So as an example, for the AI-driven network management, what is currently happening, for example, in the RAN network, we have a lot of telemetry over the E2 interface that is pushed towards some resource intelligence, like some RIC controller, which runs AI-driven control loops. And most of these AI applications that are inside this softwareized controller configure the network elements in an optimal way and update the configuration through AI models that are based on telemetry and forecasts. In order to do proactive network management, we need to forecast many, many different things, because if we have some forecast available, we can do proactive tweaking of the network to be able to prepare it in a better way to the things that will happen in the future. There's many different applications that are currently developed for forecasting. For example, forecast traffic demands of different base stations, resource availability, like G-node resource block availability. We use a forecast to do anomaly detection, to forecast user mobility, and so on. And these AI applications, they are deployed at different locations. For example, the RAPs, they are not real-time. They are deployed maybe at the cloud, and the control loop is like the order of seconds or minutes for policy management and long-term optimization. The XApps, they are on the regional cloud level. They have a control loop below 1 second, and they try to optimize resources and control the traffic steering. And the DApps, they are basically on the local edge cloud close to the hardware. The control loops is on millisecond levels, and I optimize the radio access and the beamforming in the real time. Then what we see here is there's many AI models, and the question is how to implement and update this model efficiently. So there's many, many different bits and pieces flying around to build an AI native stack in this cloud nativeness world. So you see there is Kubeflow, Apache Kafka, XGBoost, some for model LLM observability, some for policy and security, some for ML model serving, some for distributed training. But the question is, how can we use these many tools in the telco AI network in a consistent way? So that built the path towards looking for AI machine learning models and use them as a service. So there's currently something going on in the standardization in the ETSI area to make AI models deployable on large scale, repeatable, and consumable at scale, and treat model basically as managed assets, AI models. That requires the automation of the modeling pipeline. So that requires to do an AI model benchmarking, finding out which model fits my data and use case best. We need to do the data preparation. We need to do the feature enrichment, hyperparameter tuning. We train the model, we evaluate the model, do the model versioning. And once we find a good model, we need to do an AI lifecycle management. We need to decide when to retrain the model, when to redeploy the AI model, where to deploy it. We need to monitor the model performance, and we need to update this dynamically. And this is a very hard problem to solve because there is many, many different models around. It has different resource requirements. So there is typical capabilities of such AI model as a service. So we have high performance inference services required to do the quantization, the runtime optimization. We need privacy preserving learning. We need to do federated and split learning. And we need to integrate these AI models with the AI agent so that the AI agent, based on large language model, can use these basic building blocks in order to detect anomalies, reason about, and propose solution to methods to optimize or re-optimize. So how do we now find a good model? Finding a good model is very painful. First, we start with the task. What is the job of the AI model? Is it we should like to do forecasting? We should classify something. What is the data that the model operates? What is the features? What are the types? What is the success metrics? How much accuracy do we need? How fast should we do the inference? What's the cost, the maximum cost allowed in terms of energy of such a model for consumption? Then we can build and compare these models. There's many, many different models, CNN, transformers, linear models, decision trees. Then we need to validate and test the model. We need to tune the hyperparameters, compare the performance, check the speed of the inference. And then we ask, do we have enough data? Is my accuracy good? Is my speed up to the speed I require? Can I interpret the result of the model? And so on. So in order to find a good model, we need to benchmark several different ones of our data set. And that is very labor intensive because we need to build many models. We need to tune many parameters. So we want to automate this. For automating the model creation and benchmarking process, there is different things we need to consider. One is what is the predictive accuracy of such a model that we build? What is we need to calibrate the model and check for fairness. So what is the fairness of the model? What's the reliability in terms of how it performs if there is some error in the data? What is the robustness and the stability of such an AI model? How fast the model produce our forecasts? Then what's the training time and cost to produce this model? What resources do I need? When should I schedule the training on which hardware accelerator? How much memory do I use for the training? What is the cost for the inference request in terms of energy consumption, in terms of latency? And all that boils down to many, many different KPIs that we need to gather during that training process in order to benchmark the performance of these different models. So not only the accuracy is important, but also when we deploy them in the 6G network, we need to consider the infrastructure costs for the optimal deployment decision. Like how much GPU memory do I need for the inference and training? What is the energy consumption? Because energy consumption is a big thing big cost for the operators that need to train and deploy these models. And for example, if two models have the same accuracy, maybe we should use the model which has a lower inference latency or which has the lower energy consumption. Well, now the reality of the machine learning model development and the benchmarking. So what happens now in the research, there is many, many researchers that try to build their own machine learning models to build better models for the data. So they do the manual data preparation. They create ad hoc batch sizes. They do training on a single CPU in the lab computer. Then they do very fragmented workflows. What we want to go towards is we want to automate the whole model training process. We want to basically find out what is the good multivariate data set. We want to automatically train many, many different parallel models on many, many different hyperparameter tune sets on very massive cluster AI training capabilities. Then we want to have standardized data loader, unified formats, and deterministic inference so that we can basically automate everything. And we need basically infrastructure to build a native deep learning, PyTorch, Kubernetes, ML model benchmarking tool bench at scale. And basically, in order to build something like that, there are several requirements. One is requirement is we have the need for comprehensive support for a wide range of models and tasks. Then the modeling should be automated and very efficient. So we want to have a very automated process so that we don't need to do that manually. It should be very scalable on the infrastructure side and reliable to handle very large training workloads consistently. And we should be able to customize many different metrics from both the modeling, training perspective, inference perspective, and from the infrastructure side. We want to protect sensitive data during the model training process, and that should be very user-friendly. So based on these requirements, we developed some method that basically allow us to automate the data management. We want to load, for example, CSV files or from a data lake, automatically load the data sets that define, for example, our time series, our multivariate, univariate time series. Then we want to define our model architecture on a high-level language. We define, for example, for the split model pipeline, where we want to split the model. We want to select the hyperparameter scalars. We want to define all the optimizer, all the schedulers during the training process, the number of epochs. We want to save automatically all the trained models. Then we want to automatically benchmark all these models on our test or on our custom historical data set, get our model KPIs, and allow us to compare different models with different hyperparameters on the different data sets, and also create the possible pool for stacked models. And basically this we present in Infocom in May, where we automate the whole pipeline from the data collection to the model training, benchmarking, and evaluation. So we have provided GUIs, and I'll show you later some example, and YAML files where you can configure the whole automated training, model versioning, inference, KPI selection process. This is basically the framework architecture we have developed. This runs Kubernetes native. So this is our framework that we have. It creates Kubernetes training pods and basically use AIM service to basically get all the information from the training process, write the information from the training process to metadata to the model repository. We load the data from a database where we basically give the data to the training pipelines. Then we collect the metrics from the cluster via Prometheus and Kassler for the power metrics in terms of energy for the training and inference. And on top, we have developed several dashboards that show us the training process over time and the experimental configuration that you can inspect and change from a GUI. So this is fully Kubernetes native, automatic launches training inference on different hardware where you can do performance versus energy tests. So we use that, for example, for developing a new spatial temporal forecasting model to forecast 5G traffic demands on a 100 by 100 base station dataset from Milan. So with our framework, we didn't need to implement any code. Automatically, we have in our framework many, many different models. We just developed a new model, which we call HiSTM, and benchmark against this data set. And basically, the outcome of the whole pipeline within 1 weekend, you have 20 models, each one with the optimized hyperparameter, and you see how they score in terms of accuracy, RMSE, R2 score, and structured symmetrical metric. And we also see automatically the parameter count of the model, the size of the model, how much GPU memory it was required, and the inference time for the different models. So this is basically very, very fast way to evaluate your custom AI model and benchmark it against the state of the art without writing any code. You only need to write your model, and you automatically benchmark that against our baseline models that we have. Our model architectures that we have in our benchmark is many different things. So we have autoformer, I-transformer, cross-formers, we have diffusion models, we have several regression tree models, we have convolutional layer, custom RNN, we have many different loss function, we have quantile losses also for uncertainty forecasts, and additional support we integrated for split learning, federated learning, LSTM, XLSTM, spatial temporal models, and you can bring your own model by writing a single simple Python wrapper code. So you just write a config YAML file, and the config YAML file you specify, hey, how many Kubernetes worker nodes I want to use, how many training spots I want to parallelize that on. We have it integrated with a Slurm cluster who launch many different training jobs in parallel. If a job fails, it's automatically relaunched. So we can launch hundreds of model benchmarks on A100, one step after another in an automatic way. So our framework basically support distributed learning, GPU edge-aware pod placement, real-time energy telemetry collection during the training and inference process, automated split learning recovery, and fully is based on just declarative YAML configuration. And so, for example, here in this Infocom demo, we show how we automate the full machine learning lifecycle for split learning and federated learning from Helm charts that define resource limits for the Kubernetes cluster. We can use GPU affinity metrics to say, hey, this part of the split model pipeline should run on a A100, and this part should run on a CPU. We have integrated observability for energy metric collection, latency collection for the training and inference, integrated with Prometheus and Kepler. And the training pods is implemented as fault-tolerant microservices that are deployable at scale. So in the Infocom, we have basically three scenarios. The first one is to do a split learning pipeline and evaluate the split learning pipeline in terms of energy efficiency and latency, depending where we put the split point of the model. Scenario B is we inject controlled errors into our network communication between the training pods to see how the training is impacted by the network impairments. And in the scenario C, we do hardware aware agility to seamlessly swap the model between CPU nodes and GPU cloud clusters for model deployment. So for the scenario one, basically, here we have a slider implemented in the GUI where you can say, hey, your model split is a layer 2, 3, 4. And then based on that, it implements all this pipeline, automatically evaluates the training, evaluates the per container energy draw, communication overhead, activation traffic, and the edge energy metrics for the edge nodes versus the cloud nodes. And so we can evaluate different split model performance. Scenario B, basically, we inject controlled errors into our interpod communication, where we then observe the training convergence over time. We have consistent model checkpoints implemented. So if my training fails because there's too much errors, basically it will respin the training automatically, and you see how the training convergence is impacted by, for example, the latency. So what we are currently doing, we are currently getting traces from Starlink latency. We can inject and loss from Starlink from Starlink, and then we can emulate federated training over a Starlink network, for example, or over a 5G network, or over the TSN network, say, for example. And that allow everything just by a simple YAML file configuration that allow you to inject these faults and this interpod communication characteristics. Scenario C, we can easily swap the model from XLSTM to LSTM, and then basically we collect different KPIs for the LSTM. What's the convergence speed versus the XLSTM, resource utilization on the edge CPU and on the cloud CPU from the LSTM versus the XLSTM, and so on. All this through a GUI. So now you found the best model using our framework. Are we done yet? So in the current state, we have dozens of static monolithic models, and we have manual update schedules which decide, hey, this model now maybe we need to update in 1 day. And there is a very unspecified lifecycle management to update the ML models dynamically. However, on the 6G, we will have thousands of heterogeneous models across edge and cloud nodes. We have continuous real-time retraining on fresh environmental data requirements, and they should be tightly integrated with RAPs, XAPs, and DAPs. So basically, relying on the manual heuristic to update AI models may disrupt our network, and we may lag behind optimal performance. So we need automation. So I give you some deployment examples and reasoning why AI model update is hard. For example, we have a traffic steering XApp, and this traffic steering XApp learns the cell load imbalance and requires handovers to proactively push user to a new cell. And we need recalibration once the traffic mix change, the mobility change, topology change. Example 2, we have a DApp for energy saving and TRB slicing policy. So we turn carrier and features on off or reslice PRB if the demand changes. So this requires versioning across different sites and different G-Node hardware. And dynamically updating the AI models during the lifetime is very difficult because we need to detect a model drift, we need to trigger a retraining, we need to do a model hyperparameter search update, we need to check after a new version, what's the new accuracy, latency, robustness. We need the complexity of the deployability need to be managed. For example, the rollout time of the new model need to be minimal. We need to have a choice of the new model requires a GPU. Should it be pushed on a certain cloud server or the edge server? What's the energy aware placement? And we need to integrate that with the telco RAD, XApp, or DApp. On which node should we run it? And this is basically the challenge, is not finding a good model or a better model, but dynamically updating the correct model at the right place, at the right time, in the right interfaces without breaking the network. So basically, our suggestion is our framework, instead of reading the data from a database, we are going to implement to read it from a data lake or from real-time streaming telemetry. We will put our framework in a RAP. We will make a new RAP that automatically decides about AI model updates. And basically, we will need a new AI model container orchestrator to place this new application at the correct place. Basically, that is our proposal to continue in this direction. And I think I'm already very late. I have one more slide. Basically, here, give us an example that our model benchmarking gives us different models for the different apps, different versions. For example, GApp version 1, DApp version 2, XApp version 1, XApp version 2, ARAP version 1, ARAP version 2. And for example, we can see that the update from the version 1 to the version 2 increase accuracy by 2%, and the service time is reduced by 7% for the major version upgrade. For the minor version upgrade, maybe we have accuracy just increased by 0.1%, and the stability has been reduced by 0.1%. So then the update agent need to decide when it's beneficial to update which model on what algorithm to use for that, and there's different methods how to do that. That opens the way for many different future research directions. We need to basically check the model quality and optimize it over time. We need to detect the drift. We need to do active retraining trigger. We need to have a model selection algorithm. We need to compress and optimize the inference process. And we need an explicit benchmarking framework and experiment tracking. We need a systems research to do reliable and efficient deployment, Kubernetes orchestration, multi-KPI replacement, observability, fault tolerance, and policy control. And the telco research is basically functional split of the model, where to deploy them, when to update them, which model subscribe to what telemetry, what data pipeline to use, and to check the latency, compute, and SLA budget. Basically, existing solution check typically only on one pillar, but we need to integrate all the 3 pillars for the 6G. And that's a summary of my talk. So the telco AI cloud needs AI infrastructure, AI agent, model as a service, and a digital twin. Finding a good model requires benchmarking at scale. We provide a framework for that. The MLOps need to be fully integrated into 6G for continuous updating to the best AI model. So we are towards implementing something like this in order to support thousands model concurrently. And that's the end of my talk. Thank you, guys.
Thank you very much for this very interesting talk. And I guess due to the time limits, we are not able to ask people for questions. I have still only one. So it means what you have now shown is possible to be used by all of us. It means we can go in contact with you and we can ask. It means all 160 members and also other interested parties here in the lecture can ask you to test their own models, their own data sets with you together.
So, Josef, that's a very good point. So we have many collaboration, both with research teams that use this benchmarking model also for different use cases. For example, to forecast, produce power of solar panels, consume power of households. We are working with big telcos that use our framework for benchmarking their models for example, G-Node-B resource block forecasting. We have an infrastructure that automates everything on a Kubernetes cluster, on a A100, on a Gracehopper, but we can give you the training containers open source if you are interested to test that at your place, of course.
Okay. Thanks again for this very interesting presentations. And actually, I tried to follow all slides, but it's so much information. It's I guess it makes sense to watch the video, the recorded video offline in more details. Anybody here in the call, if you have any questions, any wish to contact Andreas and to talk with him about this future of 6G and this AI-based test environment and benchmark environment, please contact us. We will forward your emails to Andreas. Sorry to stop now. We have to go to the next presenter. We're already a bit behind the time, but it was so much interested. I don't want to stop. The next presenter is Andrea Conti, and he talks about AI-based localization and sensing. Andrea, careful, Andrea.
We lose an S, from
yes, sorry. please introduce yourself and start immediately with
yes.
with the
So let me share my slide also. Okay.
Yeah, sure.
The host is not working multiple presenters sharing. Maybe okay. Now I see that I can. Yeah. Okay. I hope you are now seeing my slide. If you can
we do.
confirm. Okay, thank you very much. So so I'm Andrea Conti. I am a professor at the University of Ferrara, and I'm also the director of the Wireless Communication Laboratory at CNIT. Thank you for the invitation. It's a pleasure to be with you all. And today I would like to share a few things about localization and sensing, especially AI-based localization and sensing, showing also some simulative and some simulation and some test bed results that we obtained over the recent years. So this is the outline of my presentation. Now we are short on time, so I will just give a little bit of preliminary, just in case some of you is not fully aware of what we mean by localization or by sensing, even if I expect, and what is the 3GPP perspective on that. Then I will talk about localization and sensing, touching upon aspects that relate to how to develop techniques for localization and sensing based on AI and ML. I will show a couple of videos about some results that we have, and then I will some takeaway message. In case time allowed, maybe we can talk a little bit about toward what is beyond 6G. So a few preliminaries. Location awareness is becoming more and more relevant as it enables a myriad of new applications. Here I'll just mention a few. Rather than going through this list that probably you can relate to some of them or just looking at the picture, I would like to mention that, of course, 3GPP is defining several use cases and also clustering these use cases. And we can see that in all of them, situation awareness, where situation is also formed by positional information about the users is critical for several applications. And not only location awareness in the classical sense, but also sensing, where we obtain situation awareness by interpreting the physical environment, is becoming important in several applications. Just to mention a couple, assistance of fragile people, as well as industrial environments where there are workers and robots operating in the same environment. And one of the keywords here is also semantic sensing, where the system does not only have the goal of inferring the position of the users or the machineries that are operating in the environment, but also classifying them, being able of identifying the type of target that, based on the reflection of electromagnetic waveforms, they are able to determine. The relevance of localization and sensing is also, of course, witnessed by a number of specification documents that, for example, 3GPP, but also other standardization bodies are delivering. I just mentioned a few that are kind of related, starting from the very first document that set the requirements for services based on localization, to others that are mentioned about the use cases, the situations in which there are only partial coverage instead of full coverage, more recently, the integrated sensing and communication, the role of artificial intelligence and machine learning for air interfaces, the functionalities that at the architecture level one needs to develop to allow such level of situation awareness, and then again, more recently, the 6G use cases and service requirement. Just to mention about a couple of aspects, one related to the network function and the other related to the service level requirement. In those specifications, you can see that location is becoming central. And in fact, the AMF, which is the core function for the network, directly speak through an interface with the location management function. And this location management function is in charge of controlling all the aspects and the signaling related to localization in the 3GPP view. 3GPP that also define service level requirement. I'm reporting here a table which is not divided over the 160 use cases that are currently under consideration by 3GPP, just something which is more shortened and summarizing what were the up to a couple of years ago, the service level requirement. Now the GPP is asking for even more, just to show that there are different service level requirement in terms of absolute or relative localization accuracy, both horizontal and vertical, because of course non-terrestrial networks, for example, when we have user equipment or base station that are mobile and that are posed over drones are becoming more and more important. You see that depending on the different type of scenarios described in terms of environment and velocity of the target, there are different level of accuracy. Some of them is a sub-meter, which is quite challenging with current technologies. And even more challenging is the fact that not only the accuracy is sub-meter, but also the availability, meaning what is the percentage of time that accuracy needs to be fulfilled is quite high, over 99% of the time. And not only the accuracy of the localization is of interest, but also the latency, because for some of the services or for the network control purposes, most often we need to have updates on the location information in the order of 10 or 100 milliseconds. Location awareness is a win-win situation, because on the one side we have the RAN, which is evolving also to provide improved location-based services by exploiting the so-called radio access technology dependent measurements. For example, time difference of arrival via SRS, the sounding reference signal, or PRS, positioning reference signal, even if this last one is only under consideration but not yet used by operators. Or if you are in frequency range 2 at millimeter wave, or even frequency range 3, which is in the middle between the below 6 GHz, FR1, or around 28 to 30 gigahertz, which is FR2. Now there is also FR3, which is in the order of 12, 14 gigahertz. And in those cases, you can also consider MIMO techniques that allow you to gain information from angle of arrival or direction of arrival or angle of departure measurements. But in addition to those RAD-dependent measurements, which exploit the RAN, we also need to do data fusion using RAD-independent measurements like other technologies, satellite-based, Wi-Fi, ultra-wideband, Bluetooth, or inertial measurement units, because otherwise, with the current RAD-dependent measurement, it's very hard in complex wireless environment to fulfill the service level requirement that I mentioned. But I was talking about a win-win situation, because not only the network is evolving to improve the location-based services, but also the location awareness can improve the network and the network management. For example, for beamforming or beam tracking of mobile users in the environment, for improved resource allocation, or also, for example, as Andreas was mentioning, a digital twin for an improved network digital twin, when you want to perform the digital twin not only of the electromagnetic level in terms of propagation, but also in terms of situation awareness of the entire network. Okay. Given this little bit of preliminary, what we have considered over the last few years is localization of things as a process of locating, tracking, and navigating any possible collaborative or non-collaborative nodes. Collaborative means that the nodes exchange messages and participate to the location process. Non-collaborative nodes means that they are not participating to the process. They could be, for example, unconnected devices. And we approach this by first looking at the theoretical foundation. For example, there is a lot of work that has been developed at the WINS lab at MIT about what are the fundamental limits given a certain technology and a certain environment on the location awareness. And then we look into technological perspective, which type of internode or intranode measurements, how to exploit environmental information as prior information in the location algorithm, what is the planning and the infrastructure of the network in a certain environment. Based on those, we develop algorithms, which are basically statistically inference algorithm, also based on AI and ML, as we will see, in order to obtain some generative model, for example, that in complex wireless environment is needed to approximate a propagation, a situation of the propagation that is not straightforward to study with the current models. Those algorithms need also to take into account models about the observation, the perceptual model, and the mobility. We need to exploit spatial-temporal cooperation and fuse, as I was saying, different type of technologies for application that are those that I mentioned earlier. And of course, this is the classical design loop where the application then set new requirements and these also need to determine the develop a new algorithm based on different type of technologies. I just would like to mention that the theoretical foundation in this framework are very important, not only because they give you a sort of gap to be filled, you know, how far you are with your accuracy from the best you can do in terms of estimation and performance. But the theoretical foundation are also important as a blueprint because they give you ideas on how to develop algorithm. And this is in fact what happened when we decided to move from classical localization approach that were based on single value estimates, which means you collect measurements from different base stations or access point or anchors, which are node in known position. And then based on this measurement, you perform a single value estimate, for example, a time of arrival or an angle of arrival. And you serve those to a localization algorithm that fuse them together with some prior information. This is a classical approach, but unfortunately, this approach fail often in a complex wireless environment where there is a lot of non-line of sight conditions or where is a rich multipath fading, because such estimates are affected by error. So your algorithm often is not robust enough to deal with those type of uncertainty. Instead, we learn how to exploit all the information that are carried by the received waveform, and we develop a probabilistic approach, which is called soft information based localization, where basically we do not send to our algorithm. We don't use a single value estimate, but instead we entirely use a relation that between the measurements and the possible position of the users. And this is a kind of workflow, and that relation can't be modeled by classical models that are used. For example, if you use algorithm like maximum likelihood or others, and often needs to be learned via machine learning, so with some training. And of course, the key here is to be able to have a fast online phase and a short training in order to satisfy, but that can still satisfy the required service levels. And this is fully integrated in 3GPP, in the context of 3GPP, and we have shown, and I'm going to show you a few results based on 3GPP radio resources, which are FDM signals, so according to the technical specifications, and measurements that are related to the time of arrival for FR1, as well as measurements that are related to the angle of departure. tour in FR2 or FR3. This probabilistic approach can also be used to obtain information about, soft information about the no-line of sight condition of the environment, which offer a probabilistic approach that account for both relation between position and measurement, as well as relation on the contextual information about the propagation condition. And I will not dwell into details here, but it's possible to develop no-line of machine learning-based techniques that provide you soft information about the no-line of sight condition, relying on features that one can extract from the received waveforms that are amplitude-based or time-based. So I showed now a little video where we can see a graphical user interface that we developed just to show performance. On the top left, we have a 3GPP scenario. For example, in this case, we pick indoor open office. You will see the carrier frequency, the bandwidth of the reference signal, the type of measurement that is going to be changed during the video. In the bottom left, you will see in space and time how this soft information evolve. And in the bottom right, you will see the empirical cumulative distribution function of the horizontal localization error. And of course, this is the cumulative distribution function, so the more you are to the left, the better it is. And here you see some percentile performance for soft information and for 3GPP-like algorithms. So for example, if we consider 100 megahertz at 30 gigahertz using downlink time difference of arrival, and let the video go. We will see now, okay, for example, here you see the type of measurement that one can consider. Now, you see now that the angle of departure has been selected, okay? You see that then your soft information has naturally the form of bins. The square that you see inside the environments are the G0B according to 3GPP specification. You see the two empirical CDF that evolve in real time as measurements are collected, and you can see what is the gain of soft information, probabilistic approaches, ML-based probabilistic approaches with respect to 3GPP-like approaches. Now you see also the time difference of arrival, so your soft information naturally has the form of hyperbolas with respect to the anchors, and you see what is the type of gain that you can reach in these type of scenarios. So this is just to show that given the same number of measurement is possible to given the same type of measurement is possible to obtain a significant performance improvement. Here I'm showing also some results in the indoor factory, where especially in the indoor factory, which is more challenging, where there are a lot of no-line of sight conditions, and you can see that there the probabilistic, the more complex is the wireless environment, the more relevant are the approaches based on soft information. Okay, this was just meant to give you some example of what the performance gain can be. If you are interested, we also made an open data set, which is called XGLOC, which seems to be largely using with thousands of downloads so far, and provide you with the signals and also location-based analytics and in 3GPP defined scenarios. So there is a QR code here that will be shown also at the end in case you will be interested, or you can of course contact me. So this was by simulation. Now what we will try to do is we develop an OAI-based dedicated network here in our lab, and we start to test on the real field also these techniques. The second part that I would like to mention is about the semantic sensing. We are now in the area of device-free localization, where we have targets that are not connected, not necessarily connected to the network. In such a case, we have passive target, or where we can have sources that are not dedicated to the role of sensing. And in such a case, we talk about passive source, and we exploit signal of opportunity. Of course, the difficulties here is that the inference of the position of the target needs to be done based on the reflection of the electromagnetic waves, and the reflection occurs not only over the target, but also on everything it is in the environment. So we will see that it's very important to be able to remove the clutter and associate measurements to the target. So these are the kind of key blocks that we develop based on some off-the-shelf technology for wireless sensing, some technique for target detection, some algorithm for multi-target tracking, and also identification, which together with tracking provide what we call semantic sensing. So, for example, for target detection, we can see in the range map and the range angle map, the situation could be quite crowded if we do not perform clutter mitigation. After clutter mitigation, we have a much cleaner view of what could be of interest in reflection, and then by clustering we can associate measurements to specific target. Once done that, we need the data association, because the target, of course, are moving and are also crossing their path, and we need to be able to, with again some AI ML based algorithm, to track the position of the target, and not only track their position, but also identify if they are for example, people or industrial robot. Okay, and classically, people used to identify target based on the radar cross section, but in complex wireless environment and for some type of application, this might result in performance that are not sufficiently accurate, and we find out that if we rely on Doppler signature, we can obtain a much better performance. For example, here you can see the Doppler signature of industrial, the sick vehicle or human target. So just to show you a video also on semantic sensing, to show within a competence center in Bologna, we have a MIMO radar, which is an off-the-shelf automotive radar at 77 gigahertz, 2x16 antennas. We have a person that entered the environment. You can see here a GUI. The person is first recognized and classified as human based on how it moves. In industrial environment, you might have areas that are dangerous, so you might want to start some alert in case the person enters some areas. We have this square that are 60 by 60 centimeter to show you what is the accuracy in the order of 10 centimeter. No need to say that the person is not connected to the network. Everything is based on a reflected waveform to the radar. We have had the opportunity, and we are very grateful to 16G to be able to show some scaled version of it also in some of the 16G summit. Then you can see that also the robot is entering the area, and it is identified as a MIR, as an AGV, industrial AGV. Now the robot is moving. You saw that also for a certain period of time, it was kind of stop. And even if you stop, the radar is still able to classify and localize. And the tracking happen 10 times per second, so 8 times per second, so every 125 milliseconds. And then we show here 2 tracks for the MIR, because on top of the MIR, we also put some ultra-wideband technologies to show the comparison of sensing techniques with respect to active localization techniques. Okay. And this is just to give you a sort of idea of technologically what can be done once the algorithm are developed based on theoretical foundations, so a few tens of centimeters for tracking. And I think my time is now up. So just to summarize, some takeaway message. We think that localization of things is essential for various emerging applications, 6G use cases, as well as for managing and developing AI-based radio access networks. We've been developed some AI ML-based localization techniques based on soft information, which provide much richer information than single value estimate. We've been developed some semantic, i.e. tracking and classification techniques for multimodal sensing. What I show you was based also only on the radar. We are testing data fusion with cameras and radar, for example. That part is now sensing only, but as you know, also within 1.6G, there are work items that where integrated sensing and communication are considered, and one of the talk later will be about integrated sensing and communication. And we develop a data set called XGLOC, when if you don't want to simulate entirely the 3GPP stacks and you want just to use waveform, you can feel free to use it and develop your own algorithm. And with this, I would like to again thank you for your attention, and thank you, Joseph, for the kind invitation.
Thank you very much, Andrea. Very interesting demo at the end. I was enjoying it last time in Bologna during the 160 summit. I was very much surprised that you can really accurate measure the position and also accurately distinguish between an object and a human. One question regarding this, if we talk about factories, that's one environment. Another important environment is maybe streets, because we have cars, we have a lot of peoples and also other objects like scooters or bicycles on different places on the street. Can your algorithm also distinguish between bicycle riders and maybe a human walking around?
Well, of course, we need to test. We are starting the training of different type of targets with respect to those two that I was showing, which are industrial AGV and the humans. But for example, we perform some activity also outdoor in a parking lot. So we need to do definitely some training to learn some Doppler character features of those type of targets. I believe that this is doable. By the way, just to give you some concrete numbers, so far we are in the order of 92% of accuracy in distinguishing between the human and the mirror. So there is still some failure from time to time, but we are continuously, so our algorithm continuously classify. It's not just a one-shot classification and then you have to stack with your decision. So as long as 8 times per second you determine the new position, and a few times per second you also determine, every second or second and a half, you also determine the new class for your. So we update every time, so we need some training, but I think is doable. What matters here is also how everything will scale in space and with the number of targets. And there is a trade-off between the accuracy and the number of targets and the accuracy in the classification. So of course things needs to be tested, but in those cases you might also think that you don't have only one radar. You might have multiple radar that operate over a certain areas.
Okay, perfect. If you look to the Q&A symbol on the button, you can also see that you got 2 more questions here from Yuri. He was asking actually here at the last one for device-free and semantic wireless sensing. How robust are Doppler and range-based signatures when the environment change? You can also answer this by typing in the answer, but you can also...
Definitely. Just a quick answer is that it turns out that the algorithm we develop do not require a long training. One side. The other side is that we have some machine learning based technique for clutter mitigation, which is in the order of 40 seconds. So we switch on the system, 40 seconds of empty room, let's call it, and the system is able to go. And of course, you learn things that are even if the environment is completely changed. And this is nice to see. For example, we test and we put a chair, which is something static in the environment. Okay, so if it was not part of the empty room, even if it's not mobile, you see the chair. And you track the chair, even if, as a static. But if it's part of your empty room, then you don't see it anymore. It does not disturb, it's not clutter. So, of course, which means that you really need a robust data association and robust clutter mitigation, which is what we've been working on. So far, I'm pretty satisfied, but I'm sure we can do better.
Very good. And please use the time and answer the different questions.
Absolutely.
If there are some open questions are. Thank you very much. And you are actually very good in time because you have started a bit later. I would like to hand over now to the next presenter. It's Narcís Cardona. Maybe Narcís, you are also able to introduce yourself.
You can hear me, right?
I can hear you very well.
Okay.
I will stop sharing and give you the floor.
So this is...
I see your slides. Perfect.
I think you see my slides. Okay, I'm Narcís Cardona, the director of the 6G Joint Innovation Center in Valencia, and actually the vice chair of 160 Association. I will talk you about the ray tracing when we are using game engines. And you will see that there is a lot of beauty, but there are some risks that we have to take into account. The presentation will be around these topics, so I will tell you how is the game, but more than that, which is the physics behind all these beautiful things, the data you need, and so the tool you can build, and what happens when you consider that everything is not static, but it comes to be dynamic. There are things moving around, and when you consider to have the sensing, the ISAC, just mentioned in the previous presentation, within the tools. Okay, it's not that strict. So let's go to the first part. If you don't need deterministic channel modeling, you don't need to consider ray tracing at the very end, because you may be interested in just in path loss, maybe in very macroscopic things of the channel, or you want to do system level simulations, or you just are interested in some observations of the CSI narrowband. In that case, this is a huge city in China, I think. You just need the structures, the main structures, and some slight portion of information. And then you can just launch nodes here, even moving nodes like this drone that I am dropping there. And you can, let me jump to some point, and you can have real-time calculation of the system or the network. Here you have the best server, or you can have receive power. It comes in a second. I think here, yes, or quality of service, or quality of the signal interference, whatever. So this is real-time, recalculating the network, but you are only interested in macroscopic things. But wait, if you need to characterize this in wideband channels, meaning that your bandwidth is above the coherent bandwidth of the channel, or it is dispersive, and you want to determine how much is dispersive the channel, or you want to consider the angular domain of the receiver. If you are modeling ISAC, targets are no longer simulated to regular clutter, and Doppler makes a lot of sense, as you have just seen, as well as for localization. And there is something else when you use big MIMO or antenna arrays that are bigger than the usual ones, then the spatial consistency is not warranted, and then you need to model differently than the stochastic or semi-stochastic models. How have we done this so fast? Or how can we go that so fast? Because we need to trace rays. We need to mimic the propagation of the waves in these environments. We can use, for instance, raycast. Raycast is one of the typical functions of game engines that normally run in the CPU that are used to program shooting, essentially. Yes, but raycast is normally limited to some thousands of rays. After some thousands of rays, this collapses. It's nice for a battlefield in a video game, but nothing else. Or you can use it as well for your tools if you want. But better if you have a GPU, and you can accelerate the calculations using functions like ray trace shaders, for instance. This is an Unreal Engine function. And in this case, the limitation goes to tens of millions of rays. And the CPU is not, the GPU, sorry, is not suffering. See below there that GPU is running 80%, 0% at many points. CPU is neither, but the memory, the RAM memory, because you need to read and write a lot amount of information, is now the bottleneck. It's not the computer itself or the computation capabilities of the G or the CPU. And by the way, on average, we have seen that running GPU ray tracing or ray launching is like about 20 times faster, at least 20 times faster than the ray casting CPUs. Sometimes you don't need to go GPU, but many times you do. So let's play the game of tracing rays in a big city, which is like this video will show you. And you will see that you can, in fact, track users in the scene. By the way, you will look during this presentation to some of the tools in plural that we have been developing, okay? This is more close to a video game than a real scientific tool, but it's going to show you how are we launching rays from the node to any moving obstacle in here, any moving user in here. And in this case, this is a car. And you can notice that there are a lot of rays coming from the same trajectory to here, and that the car is capturing a lot of rays around it. And this is because if we want to launch not very high resolution in the angular domain, so if we do not want to launch 100 million rays, then we reduce the angular resolution, and to guarantee that this trajectory is impacting the receiver, we cannot put here a single small antenna in the receiver. We have to allocate a reception sphere or a reception voxel of certain size. So what is the consequence? We have fast ray tracing, but with low angular resolution and a lot of post-processing and less precision, of course, because we are combining rays that are not exactly the ray that is going, or the propagation ray trajectory that is going to the precise antenna. Okay, so it has to be taken into account that there is a lot of physics that we have to consider, that not only this beauty thing of launching rays and rendering into this environment. We have to check if UTD is valid in this, uniform theory of diffraction is valid in these environments. What happens when we are near field, if diffuse scattering deserve or not to be programmed, when we consider big channels for MIMO, for instance, if there is coherence or not, if there is a spatial consistency, angular consistency, and what will we do when we are facing sensing. Let's go to the physics that are behind this, because there are a lot of things that you have to take into account if you want to develop one of these tools. First one, when we do ray tracing or ray launching, we're assuming that the approximation of GO or UTD is valid. So geometrical optics or uniform theory of diffraction are valid. You know that these are asymptotic methods that are considering that the propagation can be modeled as rays without interaction volume around them. This is good when frequency increases because the wavelength comes to be small compared to the surface dimensions or the obstacle dimensions in which the wave is impacting. And specular scattering dominates. But when we go up in frequency, let me say around millimeter wave frequencies, then diffuse scattering starts being relevant. But on the contrary, if you go too low in frequency, there are propagation phenomena that are not properly modeled with ray tracing. Diffraction, for instance. Diffraction assumes that the object is larger than the wavelength, but this is no longer true if you go low in frequency. Penetration, so diffraction through objects, is more important and plays a role in low frequencies, and also there are resonances in cavities. See the example here. This is an auditorium. We put this transmitter here. We calculate the ray tracing to that antenna over the scenario, and you see a lot of very many rays creating this propagation channel. At high frequencies, this is a very dispersive channel, but at low frequencies, if you know about microwave, this is a resonant cavity. Okay, you can perceive the resonant modes in here if we go very low in frequency. So there is a range limit, I would say between 3 GHz and 30 GHz to be on the safe side, in which these ray tracing tools can be applied with this UTD approximation. Okay, near field versus far field. I will do the following consideration. If we launch rays from this point to that, let me see. Let's see the video for a while. We are launching rays in a spherical way. So we launch in all directions from this transmitter down here. You see it here. Yes. Yeah. Here. Yeah. And we reach the positions of the users, and then we calculate the channel on the time. This is a dynamic simulation. All right. Okay. What we in fact are assuming in many ray tracing or ray launching tools is that propagation is far field, meaning that there is a planar wave impacting the obstacle and then reflecting the rays. And this will mean that we can assume for a certain range around this object that all the rays are parallel and also reflecting parallel. And this is no longer true, of course, because the propagation is spherical. If you are far away, okay, let's approach a little bit. If you are far away, you can say that locally around this reflection point, the field is planar, so you are far field, but in fact you are not. Yes, because if you go there or here, the distance and the angles of impact to the surface are not the same one. This happens. This has a huge effect when you consider arrays. If you consider a linear array here or a planar array here, the different positions in this array will face not the same angle of arrival, not the same path length, and so not just a phase shifting, linear phase shifting along the array. Okay. There is also a practical thing here, is that if we want to assume that we are far field, we have to launch rays at least to this point, to this point, to this point, yes, to avoid having to assume that we are near field. And the reception sphere that was mentioned before, and also the materials have to be characterized. Okay, for the first thing, for the angular resolution, we have established in our tools that where the receiver position is, you have to reach a spatial resolution of half the wavelength. And this, as you can see graphically here, this defines the minimum number of rays that you have to launch, or the minimum angular resolutions that you need, okay, to reach this spatial resolution of half the wavelength at the receiver side. An example of what happens when you do far field or near field is this antenna is far field from the building. This is a Congress Center because it's 60 meters at 6 GHz. This is far field, but the receiver is not. From the receiver point of view, it is not, because the receiver is, you will see in a second, The receiver is a big MIMO panel in here. Yes, call it holographic MIMO if you want. And so if you look at the, let me go to some point, this point in here, sorry. Yeah, here, the arriving rays to every antenna element are not parallel, not coming from the same angle. So we cannot say that we just calculate one and shift the phase linearly for obtaining the others. This is because we are, in fact, near field or spherical wave propagation to here. Okay, also the length of every of this path is different. All right, so many times the launching rays, so launching spherical rays, is better compared to tracing. Tracing, you know, that it is finding the reflection image of every object and tracing only one ray. But launching is, in principle, performing better for near field approximation. Okay, what about diffuse scattering? This is very popular as well. Okay, in our scenes, we have like this brick wall or the asphalt, which is not completely flat, the grass, of course, the trees, this is a different history. And if you go to literature, you will read this. You will read real surfaces produce significant diffuse scattering, so they are reflecting non-specularly the energy. Okay, this is true, but this is when the roughness is very small compared to the wavelength, and then many ray tracing engines treat surfaces as perfectly smooth and then add a diffuse scattering contribution or diffuse scattering model. That's true, and that's okay. But many times, many of these engines and many measurements that we have seen in literature include in diffuse scattering whatever cannot be modeled by deterministic ray launching or ray tracing. So diffuse scattering, this is only myself saying this, so blame on me if it's not true. Diffuse scattering is whatever you cannot model deterministically. If you have infinite resolution of this material, you can have infinite number of rays impacting the material. You can do a solver to calculate precisely the electromagnetic wave, but okay, you cannot do it all the time, right? There are some effects that you have to avoid when interpreting diffuse scattering. One is this one, antennas are not rays, antennas are sending waves according to the beam patterns, yes, or to the emission patterns, and so are projecting the antenna beams on top of the surface like this in here. So even if the two antennas are non-specular pointing the surface, there is some contribution because there is some path that illuminates this surface and goes to the other beam of the receiving antenna. When you approach, of course, pure specular, then you have the maximum of the energy. But note that sometimes what we consider diffuse is these kind of effects, and some measurements published in literature. See also something that is happening here is this notch. Yes, this corresponds to some resonance. Yes, this is because in built materials, see, this is the power delay profile of a measurement on top of a glass wall. Yeah? If you consider only the first reflection on the surface, you will have a channel that is like this, only this contribution. But there are internal reflections that the material is not just a thin layer of the material and the permittivity constant everywhere. It's built of layers. There is the brick, there is some air behind, there is some fiber maybe, there is one more bit behind it. So all these internal reflections create that resonances, and so create these secondary paths for a reflection that eventually one can say, oh, this is diffuse scattering. No, this is internal reflections, and this is causing like this. Yeah, and this also happens indoors more when we have like these wood-made walls, and there are also refraction. There are many components that are sometimes interpreted as diffuse, but it's not 100% diffuse. Okay, let's make it also for the diffraction. Diffraction is correctly modeled with UTD. In fact, UTD is for uniform theory of diffraction, but it's precise only for canonical shapes. So if you model this lamppost as a cylinder, then you have a perfect calculation of the diffraction of this lamppost. If you model the corner as a perfect wedge of 90 degrees, then you have perfect information on the diffraction. Again, the shape has to be longer than the wavelength, quite long. The tools normally do not consider multiple diffractions because there is a lot of attenuation after every diffraction. So normally multiple diffractions are usually neglected. In our case, we have put here a card and a big panel behind it to see what happens when you do not have diffraction consideration. And then there is this shadow created by the car in here. Yes, so it's blocking the line of sight and some of the reflections. Blue are reflected, red are direct path. But when we locate diffraction, then you can see that the green ones are antenna elements impacted by some diffraction from the car, around the car, or on top of it, or even below the car. So that you have these things in here. By the way, look at this. Look at this shading here. Yeah, you have like a shadow of the car and some extra information around it coming from diffraction and something else. We had also the lamppost somewhere. Yeah, so a tip for you, for if you want to analyze this and to research on this is why do they call it holographic MIMO? One reason could be this one, right? If you analyze properly or you use properly the information captured by every antenna in this holographic panel, you can reproduce the things that are happening in the middle. We did some tests in the lab. This is the anechoic chamber with mannequins. It's not a human, not outdoors, but it should work. No? This is for your next research topic. The tool needs a lot of post-processing because the raw data we generate is the collection of the thousands or sometimes millions of rays, one after the other, and the ray contains all the information: angle of departure, trajectory, material impact, angle of departure, path length, receiving, etc. So everything is in here, yes, and some post-processing is required, of course. First, post-processing, because when we are not far from the antenna, from the transmitting antenna, we are oversampling the angular domain because we are launching too many rays per degree. So it happens that in some antenna elements in the receiver, you have duplicated or triplicated, quadruplicated rays impacting. So like in this case, we have at some of these positions, we have 3 times the same, exactly the same ray coming to the same place. So we have to combine them by assuming that if they have similar delay or angle of arrival or delay and angle of arrival, then they are the same one, and we have to combine them to reach to only one box. So we do as well something interesting out of this is to understand, create, and identify clusters and so scatters. This is a 64 times 64 channel, and the rays that are coming from the transmitter to the receiver, this is ground reflection. There are 2,000 something rays coming from this point to that point. All of them are suffering almost the same delay and almost the same angle of arrival. And so we identify these scatterers. So it serves as well to identify where the main scatterers are. And note here that after this processing, we identified that, for instance, here, there is the window separate from the wall and the 2 different scatters. See the 2 different colors, very small maybe, but here, yes. So the ground floor, this building has also 2 scattering areas to this position. And so it serves us as well for this. We do a lot of post-processing. It's only in a schematic. After cleaning the data, we build channel tensors, channel matrix tensors organized by delay, by frequency, by angle, whatever. If you sum up everything, you have the narrowband channel or the CSI, you can obtain PDPs or angles of arrival or departure, whatever. So post-processing is working with this raw data in different manners. What do we need from the environment to reach that point? We need 3D or even 4D, because we need also to characterize the materials. I will jump this one to this point. We need to build 3D models and not, we cannot just extrude it from footprints. We use footprints, yes, but we build these vectorial formats in Blender or in some other Maya, with Maya. We include materials, we can classify or separate every element of the building, for instance, as an object. Objects become actors in game engines. If you program games, you know what actors means. But this is simplified in many other tools. Many tools simplify all this facade with one single planar layer. And we include detailed elements. So this is the build structure of this building in using Maya, Autodesk, AutoCAD. Then some elements are added in Unreal. This is parking access, the trash bins, the bike parking, and then we build everything. This is what the tool is using. This is what the tool is using, and this is what the interface is showing. Yeah, after rendering, you don't need this, in fact, but it's nice for showcasing, right? Materials. When you have the objects identified, every material in our tools has a reference, and the reference corresponds to a material, and the material has a correspondence to a lookup table of permittivity versus frequency, or attenuation and phase versus frequency. When we do not have it measured, because we measure a lot, we use the ITU tables. Okay? And then again, yes, we include textures and lights and so on, but this is only for visualization purposes. The calculations are done in the ugly part of this digital. Okay, this is our offices. Calibration is mandatory. You need to calibrate both the tool and the environment. If you have measurements, you can detect errors in your simulator. You are not properly modeling the reflection or the diffraction or whatever. Yes, could be. But you can also detect errors in your data. For instance, if you have a delayed path here all the time compared to measurements, it may happen that the element causing that reflection is not properly allocated in the scene. Maybe you have to shift this building 1 centimeter or 2 because there is 1 centimeter or 2 of, I'm exaggerating, right? But of error here. If you have an amplitude that is all the time causing an error, but you know that the reflection is there, it's an amplitude error. Maybe the material is not properly characterized. Yeah, so measurements serve for calibrating not only the tool itself, but the data many times. Okay, this is an example of calibration. I will not enter into this. And the best thing you can reach, of course, the blue is measurements, the red is the simulation. Of course, simulation is simulating grace, so you obtain a kind of tap delay profile. This is after calibration. Well, it's very good. You can calibrate PDPs quite well from point to point or antenna to antenna element. But the only thing that you cannot guarantee to obtain is the absolute value of the phase. Relative values of phase is fine, from one antenna position to the neighbor one, from one position to the next one. This is relative phase is fine. You know the increase in phase from one point to the next one, but the absolute value of the phase is unaffordable, because it will require a lot of a definition of the environment, the materials, and the effect of the frequency with such a precision that it's impossible to store anywhere, at least so far. Okay. Tools. I led you this comparison of tools, Siona versus some others. MATLAB, maybe you have used some of these, but for sure Siona, if you are working with ray tracing, or MATLAB, if you work with more academic thing. Okay, we have used some of them, but finally we decided to build our own tool, and this is an example of how much our tool is capable of doing calculations. Here we have a distributed MIMO scenery with 5 transmitters. In here we allocate a big MIMO panel there, 32 times 32, and it takes 1, 2, 3, 4, 5 seconds to calculate all the channels. All the channels means 32 times 32 times 5, so it's about 5,000, right, in 5 seconds. So we are getting about 1,000 channels obtained per second. So 1 millisecond to refresh every channel. Yeah, we can use diffuse scattering as well. So if you introduce diffuse scattering, the whole thing runs similarly, but it will take, let me jump, it will take some more. It will take 20 seconds to obtain sorry, not this one. Sorry, very sorry. Yeah, this one. Yeah, this one in here. All these rays in purple are diffuse scattering rays, and see, okay, that you have the same thing, but in 20 seconds instead of 5 seconds. So it's 4 times slower if you introduce diffuse scattering, but then you have this precision. Okay, and you can say, okay, Narcís, this is good, but this is static, and you have a static situation. Everything can be predetermined and calculated with some, using some time. But what happened when there is no dynamics? The first thing we did to have a dynamic simulator was to use Siona functions, but Unreal Engine interface. So and you will see this in a second. See what is happening here. Unreal is managing the scenario, creating the elements, the objects, the actors, the mobility, everything, and send the information to Siona. Siona is doing the ray tracing and giving Unreal back the channels. Okay, so it's like I take the advantage of having the Siona tool and have very quick ray tracing provided by that tool in the GPU. And then I use the Unreal for the interface and the creation. Like here, we are adding here a new base station and so on. And then we can allocate as well more users, and then the whole thing runs. Not something here is that the user moves and the channel comes a little bit afterwards. Yes, so this is the user and the channel comes a little bit behind him. Okay, this is the delay caused by the interface between the two tools. It's not that good for real time. Okay, what if we put an object here, an obstacle? Then okay, we have an obstacle here, and it is impacting. The rays are impacting the object and reflecting and so on. But there is something that we have done here, is activating the diffuse scattering. This is why there are a lot of rays. We activated the diffuse scattering because a small object like this, a car, is small compared to the environment, is defined by like 1 million polygons maybe. And if we have to do a specular to every of these million polygons and precisely go to the normal that reflects to the receiver, it's very hard. It's computationally it's impossible. So we assume that diffuse scattering is enough to give us an approximate angle of departure. But this is because we are working with the limitations of Siona. There are no refraction, no crossing the car anymore. Somehow
sorry to jump in. Could you come to the end somehow?
Come to the end?
Yeah.
Okay. Yeah. So yeah, you just see some of our videos here. This is real time with number of users. This is also real time with obstacles. Yes, and including or not diffuse scattering. I started late. Josef. Have I consumed 20 minutes already? Okay.
Yeah, it's the time is already over, but it's so much of interesting. I don't want to take away the time from the next speaker, as if you can roughly go through.
Yeah. Let me just take 1 minute to say you that we do model the sensing, the ISAC, but to model the ISAC with ray tracing, we have moved to this multiple scattering center target modeling. You can check our publications on this. With measurements, solvers, we determine the scattering points to define the model of this object instead of the polygons. A lot of measurements, and we determine the scattering centers of the objects. And finally, we introduce it into the tool. This is what is happening inside the tool. And you have the 4 channels, the 2 monostatic and the 2 bistatic promptly. So with almost in real time when you use multi-scattering center. Yes, and there are a lot of proofs of concept with measurements that with very good agreement between simulations and measurements. And I leave you this list of reference where everything I have mentioned is explained. Very last one. This is what we have. So we have tracing tools, field measurements, databases, etc. And what we can offer, and I'm inviting you to come to the 160 Summit in September in London, is the ISAC dataset. We have built this big ISAC dataset of ISAC channels based on measurements to calibrate the simulator to obtain the multiple channels, including objects with the MSC. So if you are interested in cooperations or in using this dataset for some of your researchers, for your research, we are happy to discuss, as well as the MIMO channels data that we can generate with the real ray tracing tool. So thank you very much. That's all.
Thank you very much. I don't want to, we don't have time actually for questions, but maybe you can see in the Q&A box that there is one from Finland, and they're asking about tools, and I guess you have already given an overview about this. Thank you very much. I had actually one question. It's about this reflection of human bodies, because I'm never clear. Do I see a dress? Do I see a skin? Do I see a bone? If we talk about ISAC of humans, because humans are complex structures, and they are not made on concrete, not made on metals, they are complex. And I'm never clear what do we really see if we do measurements. But maybe this we can discuss also in the working group 4 later on.
We have measurements of humans of different kinds, and of reflection and mono and bistatic. And that's, of course, that we are dielectric, we are not that metallic. Very difficult to model with a specular thing. It's a diffuse scattering anytime. Yeah. I will answer the questions in the chat.
Okay, I invite you to the working group 4 next time. Okay, let's start. I guess Mohamed is already looking what he can do. Mohamed is the next presenter. Sorry, Mohamed, for taking away some time. I hope the participants can stay a bit longer to finish your talk, even if it is 10 minutes longer as planned. Mohamed is from the, actually not from some Munich research center of Huawei. It's one of the biggest research center in overseas, and he is 6G ISAC-based environmental sensing for mapping, monitoring, and reconstruction. Please, Mohamed, take over the floor.
So, yes, thanks, Josef. Do you see my slides
yes, we
now?
See.
Okay, super.
We see, yes.
So, hello, everyone. So, this is Mohamed Gharba from Huawei Heisenberg Research Center in Munich, Germany. Today, I will present our activity about the 6G ISAC-based environment sensing for mapping, monitoring, and reconstruction. So, here is the table of content. I will start with the introduction of the 6G centimeter wave ISAC system. Then I will present our demonstration about the environmental reconstruction of city towers conducted in Bologna, Italy. Then I will show some test cases for multi-object and posture detection performed in indoor and outdoor in our lab premises. And at the end, I will talk about the micro-displacement sensing of towers test performed to monitor the Bologna towers. So ISAC is emerging as a key technological pillar of 6G wireless networks. enabling joint utilization of spectral, hardware, and signaling resources to support environment sensing alongside with the data transmission. ISAC is intended to enable the collection of information about a remote object or its environment and various properties, even without physical contact. With ISAC, we can reduce the hardware costs through the sharing of the same OFDM waveform and the same hardware. Also, we can increase the sensing resources through sharing the same signaling resources. And also, we can enhance the coverage through the full array analytic beamforming technology. By such good configuration, we can get good sensing accuracy and high capacity data transmission. For example, by adjusting the target number to, for example, 10 objects, and having a distance between 5 to 8 meters to the antenna, and having a transmitted power of 10 dBm, we can reach a ranging accuracy of less than 5 centimeter, and angular accuracy of less than 0.6 degrees, and average throughput of around 3 gigabit per second with 64 QAM. So here comes the 6G centimeter wave ISAC system, where we present the prototype system for indoor and outdoor environmental reconstruction. We begin by introducing the system architecture. So the prototype system is a monostatic sensing setup, as depicted on the right side of the slide. We have the active antenna unit, the AAU, consisting of an RF board and an antenna, which is responsible for the both RF signal transmission and reception. The antenna is designed to meet the high-resolution sensing requirements. The antenna elements are arranged in an L-shaped configuration like we see here in the figure. So the red elements serve as transmitting elements, the blue ones are receiving elements, and the gray elements are dummy elements. This configuration allows the antenna to achieve the desired azimuth and elevation resolutions while using a minimal number of RF channels, making it a cost-effective solution. So in total, there are 32 transmitting elements and 32 receiving elements. The baseband unit handles the baseband signal generation and reception, as well as the analog to digital and digital to analog signal conversions. The prototype system operates in a MIMO sensing mode, where each transmitting element sends a burst of signals in every time slot, while all receiving elements capture the corresponding echo signals. On top of that, we can see a camera which is mounted on the AAU to visually capture the environmental object detection, providing additional context to the reconstruction process, mainly for the visual verification of the ISAC measurements, saying the point clouds. So the system operates at a carrier frequency of 10.2 gigahertz with a signal bandwidth of 400 megahertz. The key specifications of the system are detailed on this table as depicted on the left side of the slide. So here we can see the ISAC process flow in our prototype system. We start with the wireless RF sensing, where the system transmits OFDM signal and analyzes the reflected echoes captured as a channel impulse response. Then we perform the point cloud reconstruction. So within the channel impulse response, the system identifies stable reflections originating from the target structure at a specific calibrated anchor distance, which are translated to point clouds, reconstructing the target object. Then comes the AI analysis of the sensing target. In this step, the targeted object is identified with the help of AI analysis, classifying the target object. Then based on the object identification and following the classification process, we have the 6J transmission of action command to the target, where the right decision and command is implemented through the 6J network. To perform the 5J, to perform the service delivery at the end for the right scenario. In the next slide, we will discuss a different type of sensing test conducted using the 6G ISAC centimeter. So we have here the large-scale outdoor environmental reconstruction. We have the multiple object reconstruction, outdoor test in Munich, human posture reconstruction, and also antenna tilt failure detection by ISAC. So let's start with the reconstruction of the Bologna Tower, the Galizenda Tower. In this work, we have demonstrated the feasibility of the 6G sensing for environment, reconstruction, and monitoring through field trials. According to our knowledge, it was the first large-scale outdoor proof of concept. This work has been carried out in Bologna in September 2025, with the aim of contributing to the study of the health status of the medieval Bologna towers, verifying their conditions through the use of the 6G ISAC centimeter wave technology provided by Huawei in FR3. This measurement system allowed for a close observation of the external wall configuration of the towers and the detection of anomalies, such as changes in the tower slope and vibration. This demonstration activity has been presented to the municipality of Bologna to show the results and provide precise support guidelines for any restoration interventions. And the main challenges here are the continuous measurement of the inclinations by 6G sensing and to complement the database for the reconstruction of the large-scale building. To estimate the inclination of the Galizenda Tower, we have reconstructed its north face. We see here the north face and also the east face, which were the only accessible sites during the measurement campaign. For each phase, the point clouds were collected at 3 different antenna heights, namely 2.8, 7.3, and 10.5 meters from the ground. To obtain a complete representation for each phase, the point clouds were stacked along the height. After the individual faces were reconstructed, a rigid alignment was applied to merge the north and east faces in a common reference frame to achieve the final tower reconstruction. To estimate the inclination of each phase, a series of plane fitting experiments was performed under different conditions. The point clouds were filtered with different reflectivity thresholds to suppress low confidence detections and reduce noise, allowing the evaluation of their impact on the stability of the estimated inclinations. We can see here in the next slide the GUI used during the demo. On the left side, we can see the live collection of the sensing data, which is represented by the green point cloud. And we can see in the right side illustrated the 3D reconstruction of the Galizenda Tower in this scenario. We could successfully reconstruct the Bologna Tower, and at the end, we could measure the Galizenda Tower slope with an accuracy of almost 96%. The tower's tilt is not uniform along its height, but rather different sections exhibit different angles of inclination. The tilt should increase with height, and the lower sections will usually show a smaller tilt than the global value at 48 meters. In the slide, we can see some collected samples from the ISAC sensing at 10.5 meters from the east side of the tower and from the north face. And by combining them, we can get the 3D representation of the Galizenda Tower at this section. And here we can see some matching between the 3D point cloud and the tower body itself. So the right side, we have the tower itself, and the left side, we have the 3D reconstruction. We can see here strong reflection, especially from the metal parts of the tower. And we can see it clearly here in the 3D reconstructed tower. So the final point cloud is affected by adjusting the threshold of the reflection coefficient. And we can see that by filtering non-relevant points, we can get a clean reconstruction from the initial reconstruction, which includes reflection from non-desired neighboring objects. And this has also impact on the collected data volume. Next, we can see that with our 6G ISAC prototype system, we can detect multiple objects like a human, like a robot, and others. And we can get the range, you can get the distance between the monostatic antenna, from the distance from the antenna to the target object. And also we can get the horizontal and vertical difference between the objects, between the detected objects. Also, we conducted some outdoor sensing where we could detect a human, we could detect also scooters and trees. And we also have performed a human tracking. So a human walk, and then the point cloud is being updated live to detect and track the human. So all is about careful setting of the window of interest and the field of view. So we have also conducted a human posture detection. We have recognized different human postures. So we have here human standing. We have here also a human shaking hand. Human is sitting, and then empty chair. So each scenario is reconstructed through the point cloud, then processed and classified using the AI recognition. This scenario is beneficial also for human and robot interaction. And in this case here, we have conducted 6J ISAC sensing to some objects in the lab with different antenna tilt angle. So we have repeated the same test with different antenna tilt angle. The idea is to show that the capability of the 6G ISAC to detect the difference or the failure of the antenna tilt angle due to the earthquake or to any other natural disaster. So with a different antenna tilt angle, we should get different reconstructed point cloud from the environment. And by comparing these different point clouds, we should detect the difference in antenna tilt angle, which is beneficial also because we will not need to send a team to the antenna site. Also, we have conducted outdoor sensing from the office window, and we have faced the antenna to the outside, and we could detect some, I would say, objects. So here we can see that we can detect almost 7 point cloud clusters. So we have 1, 2, 3, 4, 5, 6, and 7 here on the top of the slide. And then when we compare to the image from the camera on top of the antenna, we can clearly match the object outside of the window. So we can see that the cluster of 1 until 6, they represent trees. And the cluster number 7 here, it represents a vehicle. We could also be able to detect objects until a distance of 40 meters from the antenna. So this kind of test had the same purpose also to show the capability of the 6G ISAC to detect the difference or the failure of the antenna tilt angle based on the difference between different collected point cloud. Finally, we discuss here about the micro displacement sensing of the two towers. So to understand the background, we have to know that the primary excitation source for these structures is urban traffic, which generates persistent low amplitude vibrations in the range of 10 of power 3 to 10 of power 2 J. These forces translate into minute sub-millimeter physical displacement of the towers. A significant structural risk arises from the potential for resonance as the tower's fundamental frequency of approximately 2 Hz overlaps with the vibration spectrum induced by traffic. Over time, these repeated low-intensity cycles can induce masonry fatigue, posing a latent threat to these invaluable structures. So the core sensing mechanism of the ISAC system relies on probing the target structure with a standard OFDM communication waveform. The system transmits this signal and analyzes the reflected echoes captured as a channel impulse response. Within the channel impulse response, the system identifies stable reflections originating from the target structure at a specific calibrated anchor distance. The true innovation lies in converting minute signal phase variations into physical displacement. The phase of an electromagnetic wave is directly proportional to its travel distance. By continuously monitoring the phase of the signal component corresponding to the target, the system can detect any movement that alters the signal's travel path. Rearranging this principle allows for the precise calculation of the displacement. This allows the system to calculate sub-millimeter movements with high precision, transforming a wireless communication signal into a highly sensitive displacement sensor. So the architecture is based on a software-defined radio wideband transceiver. The key specification of the system are detailed on the left side of the slide here. Of these parameters, the 400 megahertz signal bandwidth is particularly significant as it provides the high range resolution necessary to precisely distinguish the reflection from the target tower from other objects in a cluttered urban environment. So here, to summarize, here the processing chain for the micro displacement sensing to extract the high precision displacement data from the received wireless signal. So we can see here the signal reception. We start with the signal reception, then we have the distance calibration, then OFDM channel estimation, and then channel equalization. Then we have the micro displacement analysis, and then finally we have the data visualization. The system was deployed on site in Bologna to monitor the Asinelli and Garisanda towers. The environmental sound noise was recorded simultaneously with the ISAC measurements. This detailed analysis revealed a clear difference in micro displacement of the tower between night and daytime. The result demonstrated a clear and consistent correlation between urban activity and the structural micro-vibrations of the historic monuments, validating the technology as a powerful tool for non-invasive structural health monitoring. And then, in addition to the outdoor test at the Bonnet Towers, we have also performed indoor tests in our lab. We have implemented the micro-displacement sensing to detect the window blinder movement affected by the AC winds. So here we can see on the left side, we have the window blinder, and on top we have here the AC. So when the AC is on, the air stream blows the window blinder, and we could observe millimeter level movement of the window blinder. We have tested with 3 different AC wind levels. So we can see here, when the AC is off, we have no movement. Once we turn off the AC, we can see some kind of vibration, and then more strength of the AC wind level, we see more movement, and then at the level 3 we have the highest movement of the blind of the window blinder. So at the end, we summarize our activities. So we have developed environmental reconstruction methods for outdoor and indoor. The field trial results validated the feasibility of environmental reconstruction and monitoring using the SecJ ISAC. The success of this deployment highlights the potential for using ISAC as a remote all-weather monitoring tool capable of providing continuous data streams and the ability to achieve these high-fidelity results without any physical modification or sensor installation. Yeah, that's all from my side, and thank you. If you have any questions, please feel free.
Yeah, Mohamed, thank you very much. This was a demonstration of measurement, what you did in different areas and for different use cases. Actually, this last presentation rounds up a bit what we all together in these 4 sessions have got regarding 6G functions and features. As Narcís in the previous talk has explained, reflection coefficient, reflection properties of objects are very complex and not so easy to forecast. And based on the measurement, what you did, Mohamed, did you found out that that it's easy to get if you look to the human and do you have a picture with multiple objects and multiple use cases? I guess one back. This one, yes, no back. Yeah. Here, okay. Yeah. You have different objects here, and you have to distinguish objects. You have applied AI to understand which cluster of points belongs together, right?
Yes, exactly. So the idea is to use the AI to classify and to identify the objects. So we have also used the AI also to classify and to identify the position of the human. So we can detect if human is standing up, or is he also shaking hand, is he sitting, or we have no human in the area. So we first collect the point cloud, and then we use the AI to process and to identify, and then we try to classify what we have collected and detected.
Mm-hmm. If you go, you have at the very beginning a sequence of processes shown, and I guess that's that one, yes.
Yes.
And you have also said that the data are shared with 6G.
Yes, exactly.
Are all data shared, or just few, or which kind of data has you?
So we share here 2 kinds of data. We share here the raw radio data, the channel impulse response, the received data. So anyone is interested could post-process the raw data. And in addition to this, we also perform a kind of post-processing of the data to generate the 3D point cloud. So we have here a second kind of data, the generated 3D point cloud of data. So we have shared with the 6J shared folder the first data, which is the raw data, and the second kind of data, which is the post-processed 3D point cloud data. So both are available for some tested scenarios, and they are all uploaded to the 6J shared folder.
Mm-hmm. Thanks. Because this links me to the presentation from Andrea Conti. He has also shown that his team has shared data measurements for the public use. I would like to ask the audience here to have a look to it if you are interested. Second, Narcís was also offering that he will share soon measurement data for all of you, because all of us, we depend more and more on the quality of measurements, of the quality of high performance simulations, and because just using the parameters from the I2 table, just using channel models from 3GPP don't show the full realistic reflection of complex objects. And keeping this in mind, please consider to become member of 16G if you are interested to work here together. If you are interested to join our activities in different means. I have at least a last slide before we stop the session. It's already a bit late. And thanks for your time and to staying here on board. Yes, also thanks first to all of the 4 presentations. It was really great to see this huge variance of work, what has been done within 16G, but also outside. All of this is very, very important to drive 6G forward in different means, and ISAC will become one of the, let's say, new legs of the new radio generation. It's not just communication anymore, it's also just kind of environmental perception in different means, whether it's with microdoppler or whether it's with detecting point clouds and more visual impressions. I would ask all of you to, if you are interested in all of our work, to check out the white papers of 16G, to if you are interested to contribute or to be more involved in the working group 4 activities regarding prototyping and testing and verification, please send the email on the working group 4 email list. If you are not member, please join 16G. It's really not a big deal. It's easy. It's for free. Not for free. You have to read many interesting things. Regarding working group 4, we planning and we have already running a lot of proof of concepts and testing. And we also build a database of proof of concept and testing capabilities of the member that should allow all of you, all of the interested teams to identify who can offer something for a joint work, like Andreas' AI platform, Andreas' platform to evaluate the quality of data, what he has discussed in the very first presentation. Also, check out 16G. Be open to work together with us on ISAC, on agentic networks and robotics for 6G or with 6G, but for sure not robotics for mechatronics. That's not our business. Thank you very much for joining this session, this open lecture. If you have a good impression, please talk about this with your friends, and later on you can share this recorded video to all of you.